Hi there. My name's Jason, and I teach at the British Columbia Institute of Technology in the Technology Teacher Education Program. And one of the projects that we like to do with our students is the Tethered Mini Sumo robot. And this is a Tethered Mini Sumo robot right here. I've been doing it with students for probably 20 years now. It seems like a lot. But it's a fun project, keeps people pretty engaged in their classes, and gives us a chance to talk about a lot of classic manufacturing and fabrication technology and things that you need to know in order to be fluent, competent in the world of technology. So a couple of those skills, I think sheet metal work is probably a pretty important one, but also the drawings that go into creating sheet metal. Now, this project's kind of aimed at the grade 9, 10 level. We're not going to get that fancy into fancy sheet metal working technology, but there's some really cool drawing techniques out there. If you look up intersections and developments, that sheet metal workers are just like, we use it every day. It's pretty common. But when you're introducing students to maybe their first project in a metal shop or a machine shop, and their first project using sheet metal, this is how I went about it when I was teaching at David Thompson Secondary in Vancouver. Now, this is an example in my hands right here. You can see it on the other screen of a typical size for a tethered mini sumo robot. I've used the Tamiya twin motor gearboxes a lot. There's also a double gearbox that Tamiya makes, and this one's slightly shorter and wider than the twin motor gearbox. They're about the same price. Has some different gear ratios on it, and I'm going to have another video where I talk about the different gear ratios, selecting the right gear ratio, and matching the gear ratio to your wheel diameter, because depending on the performance you want from your robot, either a large diameter wheel or a small diameter wheel can really make a difference in how your robot behaves and how you have to design it, because you do have design restrictions that everything has to fit into. And you also have performance characteristics that are largely determined by the motor and your gear ratio and the diameter of your wheels. So there's a lot to think about there. Not going to talk about that in this video. I am just going to talk about the drawing. Now, I am also going to be talking about drawing a robot that has flat sides all around that can be fabricated using pretty standard sheet metal folding techniques. Probably one of the nicest tethered mini sumos that I've seen, either from my BCIT students or my high school students, was made by a student at David Thompson Secondary. He handed this in to me when he was in grade 10. I asked him if I could keep it on display at David Thompson, and I meant to give it back to him when he graduated, and then he went and graduated and never came back. So if you're out there and you recognize this, I have it. It's at BCIT, and I'd love to return it to you. You'll notice it's got a rounded surface on the front right here. And that can obviously be done with sheet metal work. However, this student did have some help from his dad. His dad's a machine shop technician. And you'll notice that the TIG welds are also very nicely done on here. So they had a really good father-son weekend out at a pretty high-tech lab putting this together, and it was really a delight to see. I didn't try to pass it off as anybody else's work. It was all honest and above board, and it's always fun when you get parents like that in your shop who can share some of their skills. You don't have to go with Tamiya gearboxes. They're a really good solution because they've got two motors in there. You can also get these little TT gearboxes that are Arduino smart car motor. You sometimes see them advertised as. They're about a 48-to-1 reduction gearbox, similar size and power motor to what you have. And you could use this with the same drawing technique as we're going to use for the Tamiya gearboxes. But I've been using Tamiyas for 20 years now. If you're buying them in Canada, I suggest buying them bulk from a company called Borgfeld. That's with a DT on the end. Borgfeld. You go to their website and check it out. And that's where I like to get them. But again, that information's not really relevant to what we need to know about drawing these things. So Usually when I was doing this with my students, we'd get to a point where we'd start the year. And this would be the way we'd start the class because at the beginning of the year, counselors are still moving students in and out of classes, trying to balance class numbers and class composition and get everything set up. Students are like, oh, I got Mr. Brett, he's going to make me work. And they'll be wanting to get out and go take choir or something like that. New students show up from time to time. So I don't like to jump into all of the big tool using stuff in the first week of classes because you've got all your safety tests to do, and the students who come along in the second week of classes have to go through that. So I like to start off with some drawing exercises. So before we even get to this point where we're talking about drawing the tethered mini sumo, the students will have been through a number of exercises where we take a couple of Lego bricks, and I don't have Lego bricks right here, but you give each student 2 Lego bricks to start with, and you have them put them together in some kind of random orientation. And you set up a sheet of paper and you say, okay, let's take a look at an orthographic drawing. And you start doing orthographic drawing on the Lego bricks, just sitting at the workbench or sitting at the classroom desk. We had both in my shop, but worked out really great. We also had some drawing boards made up, wooden boards, big enough to get an 11 by 17 sheet of paper on and hook a T-square over the edge. And so that really made drawing go smooth, and every student had a little bit of space and we could get in there. Now, it's important that you don't just jump in at this stage, okay? Especially if you're working with grade 9 and 10 students, because a lot of grade 9 and 10 students have not been shown how to draw a straight line properly before. You doubt me, but they haven't. Okay, and a lot of them also don't appreciate that when you're doing a technical drawing, and I never refer to this as drafting because there is a drafting class where they use AutoCAD software and uh, much fancier drawing techniques. And this isn't drafting. You don't want to take your enrollment away from your drafting class. This is just a technical drawing. It is the language of technicians, technologists, and engineers all over the world. And so knowing how to create a basic orthographic drawing is fundamental to technical literacy. A lot of schools like to talk about literacy, but they're only ever talking about written literacy, not drawn literacy. And this is a very important part of literacy because if you can't communicate with an orthographic drawing, you can't communicate in the world of technology. Okay, so anyways, we start with doing these little Lego bricks, one stacked on top of the other, and then they get more and more complex until the students get an idea of what a hidden line is and how things go together. So when it comes time to create the tethered mini sumo robot, I have them do some design sketches and think about what's involved. I talk about some of the restrictions that they're going to be faced with, how it's got to be 10 centimeters by 10 centimeters at the maximum, and it can't weigh more than 500 grams, that you've got to have your batteries on board and your controller is going to be hooked up here. This was a different design that we had hooked up. We're not going to have a printed circuit board on it. We're just going to have a battery pack on there and a gearbox are the two fundamental things that you have to have on your tethered mini sumo. And the ultimate goal of the tethered mini sumo will be to push someone else out of a ring. Now, before you get started, and this is important that you tell your students this, if you want to create a clean drawing, you have to have clean tools. So take your squares and feel free to make the joke about the fact that this thing that doesn't really show up well there. Transparent thing. This transparent thing that you can't see that looks like a triangle is actually called a square. And you can explain to them why it's called a square and why you've got 2 of them. And if you've got a T-square, that's great too. It's not a square either. Make sure they clean off their work surface. Okay, get everything tidied up and wash their hands. Make sure they've got a sharp pencil nearby. I prefer a mechanical pencil, but a sharp pencil, blow the graphite off the tip, blow the lead off. And if you're going to be using an eraser, and I guarantee you at some point you're going to be using an eraser, make sure that it's clean on the end. You'll notice that erasers tend to get dirty as well. So take that moment and tell your students how to do a good job. Okay? They're 13, 14, 15 years old. They want to do a good job, but if you don't tell them how to do a good job, they're not going to do a really great job of it. So, okay, let's take a look at how we get started here. Now, what I'll typically have the students do is tape down their piece of paper and just a little bit of tape in each corner. Now this, if they're working on a drawing board and they've got a T-square, this is really nice because you can tape the piece of paper down square to the drawing board. We don't have that here on my desk. You might not have that if you're doing this at home. So we're just gonna say this is square to the camera, but you don't want it floating around. You don't want the edges getting caught on things. And there we go. Now, grab your squares, and now let's start with this one right here. And what I'll do is I'll line that up along the top edge, and I like to give myself a little bit of a border. And you'll notice I'm not getting really, really uptight about that border and what its spacing is. But I always tell the students that the border should be in about far enough that if you use a 3-hole punch, you don't put 3 holes smack into the middle of your drawing, because that would just be ugly. And we are trying to make something that looks half decent. Now the nice thing is, at this stage you do want to take time to try and get each of these edges square, because we will be using them as a reference later on and for our other lines. Oh, look at that. See, I've got dirt right down there. I had everything cleaned up before I started, and that was going to leave a smudge on my drawing. So get that cleaned up, and make sure your students actually have clean tools to start with. Now, as I'm setting this up, you'll see that I'm getting things lined up right along here. And if I've gone around and done that all right, this edge right up here should come out pretty close to square. Good. Okay. Next thing I'll always have the students do is come along and put a little title block in the bottom corner. So pick a square and just come down right here. And usually name, date, and title is enough for the title blocks that I have them do. And again, I'm not really going to get too fussy about the font, and but I will get them to draw 3 lines right about like that for name. Okay, put the full name on there, date, and today is December 23rd. Mini Sumo. Okay, so it should be legible and it should be neat. It doesn't have to be drafting quality, okay? This is a shop drawing. It's a technical drawing. It's one that we're going to use. It should have fundamental things so that if you lose the drawing, it comes back to you, but it doesn't have to be too fancy. Now, when you've got your piece of paper laid out and things are neat and tidy, you can actually get on to the first part of doing your Tethered Mini Sumo drawing. And the first part of your Tethered Mini Sumo drawing is to say, right, my Tethered Mini Sumo, I'm going to draw it on here, and I'm going to have a side view and a top view. So again, if you're thinking about orthographics, and if this is your top window right here, then your side view window is going to be right down here. Okay, now your top view window is going to be where you set in your 10 centimeter by 10 centimeter size constraints, because That's when you're looking down on the robot from the top. So this is where you want to come along and say, okay, I'm going to have some size constraints coming in right here. Let's get this squared up. And I find somewhere just a little to the left of the middle of the document works out okay. Somewhere right in there. I've squared this up along the bottom. Keep that drawing nice and clean. I keep getting little bits of rubber in there. And then just a faint line right down there. Then take some kind of measuring stick and measure over 10 centimeters. Right there. Line the corner of your square up with that. Faint line down like that. And then from your top view, just set it in a centimeter or so from the edge. You don't want to go too far, depending on how tall you're planning on making your robot. We're just setting some outlines for it right here. And then, I don't even know if that line's showing up right on the screen. I hope it is, and there we go. Now, sometimes if you want to get a really precise measurement, you don't measure right from the end because the end of some rulers get a little gummed up. So I'll measure from the 25 right here. And I'll come down to the 15 right here. Okay. And did I do that right? 25 to 15. Wow, what do you know? 25 minus 15 does equal 10. And then we'll come along right in here. Get this squared up again. And draw a line right there. So now this is going to be where we can see our top view. Now, few things that I've observed over the years of doing tethered mini sumos with students and telling them how to draw them. And these are critical points right here. Number one, start in the side view. Okay. And in the side view, draw a line representing the ground. This line down here is really critical because that tells the students where the ground is. Now, before you get to this point, you have to have done the calculations on what sort of gear ratio you want and how big you want your wheel diameter to be. Because the very first thing that you have to draw when you're drawing a tethered mini sumo is you have to draw the wheel. Now, if you've got a compass, that's really nice. You can just put it down and spin it around, and there you go. You've got your drawing. If you don't, you can have something else. Find an object that's the diameter of the wheel that you want. Maybe it's the outside of your otter spool. Maybe it's the inside. Inside would be a bit awkward to draw. Might be, well, okay, not the diameter of that roll of tape, but find something that's going to work. If you can't find one that's the exact size of what you're looking for, you can hack it together. And I'll show you that for just a moment here. Let's say that we've decided that we are going to go with a wheel just a little bit bigger than this one. This one is outside, 25. We're going to go with a 30 millimeter diameter wheel. Now, this is the side view of our robot. Okay, if we go with a 30 millimeter diameter wheel, then everything has to fit inside here. So this is as far back as we can go on the robot. And this is as far forward as we can go because when we draw our top view, everything has to fit into this 10 centimeter by 10 centimeter square right here. So if we're going to put a 30 centimeter wheel on our robot, we better come in a little bit from the back because you always want to convey to people when they're building robots, don't build right to the edge. If somebody gives you 100 millimeters to build your robot, only use 97 of them because something when you build it is going to be offside. Maybe only use 95. Give yourself room for error because things will shift and bend and flex, or you'll go back to fix something, or you'll want to add a nut or a bolt to it and you'll be outside your parameter. I've done a lot of robot inspection over the years, and it's it's sad when people build right to the limits and then discover that, oh, now we're oversized because something went wrong. So always build a little undersized. So leave yourself maybe 5 millimeters at the back. And then if you're putting a 30 millimeter diameter wheel on there, give yourself 15 millimeters right there. And then come down here and give yourself another 15 millimeters. Okay, so there's your 30 millimeter diameter wheel. And then you can come in right here and square this up. Now, if you're having problems squaring things up, remember that there's a couple of tricks that you can do to speed things up. You can take one of your squares, line it up and get it absolutely perfect. Hold that down with one hand and just faintly, ever so faintly, there's one edge. There's our center line. There's our back of the wheel. And again, if you've got a compass, life gets a lot more simple because you can just come along and now measure up 15 millimeters right in here to get that center point. And now you can just take your compass and spin it around in there. If you don't have a compass, okay, keep that dirt off of there. Start at 15 and let's just come up to 18 right here. That's going to be the top. And now it's just going to be a matter of coming in and marking things up. One axis aligned right here, nice and square. Bring that up. And there's one point right on there. And if you really want to get fancy, come in right here and you can. Now again, I am doing this because I'm pretending you don't have a compass kicking around. If you've got a compass kicking around, your life just gets a lot easier. Okay, line right in there. Make sure you stay on square. And then measure out your 15 millimeters on either side. Now, as I'm doing this, I have to admit, when I was a student at BCIT, we did a lot of manual drawing. And I think I was pretty vocal about my opinion that it was a bit bogus. Because who does this sort of thing with manual drawing anymore? I was all about computers and CAD, and of course I knew what I was talking about. And then I got out to my school where I was teaching and discovered that although there was a computer lab, it was booked solidly by other courses. And that my students didn't know how to draw a straight line. And that was a really classic skill that they could pick up, and the attention to detail that you could pick up from doing a little bit of manual drawing was actually a pleasurable experience. And I think they've left the class feeling that they'd learned a lot more about how to make things than if they'd jumped right into the computer. Now, to be fair, I still use the computer a lot, and I'll show you how to do some of the sheet metal work in Fusion 360. A lot of the 3D parametric CAD programs have excellent sheet metal tools. But there we go. Right now, I'm talking about how to draw a circle without using a compass. And I'm not embarrassed by that circle. It's not quite as good. You know, if you've got the compass, you just come in and of course, life is simple. But you don't always need to have a compass because you don't always have one. So that was rule number one, that the wheel has to touch the ground right in there. You have to say that. You have to demonstrate that, and you have to point that out, because otherwise you'll get random things all over the place. So the wheel must touch the ground. The next thing that you have to point out that is also not immediately apparent to students who are doing their first design project is that the axle has to line up with the center of the wheel. It's very frustrating for the students when they're doing their design to discover this, because they've got all sorts of plans for how they want to build their tethered mini sumo robot. And this gear, oops, yeah, quality assembly on there. The students don't always want to put that gearbox right in line with that axle, because man, it would be so much easier to put it somewhere else. Yeah, wheels don't work that way. Axles don't work that way. Now, the trick for getting these things aligned is to have a sheet or a handout ready to go for them that has a one-to-one scale printout of their gearbox, whatever gearbox they're going to use. I mean, you could have the actual gearbox there. So sometimes I'd have the students build this first so they'd have a physical manipulative, but you don't need that. Yeah, in fact, if you're doing this from home right now, you could go online, Google Tamiya gearbox, and you'll get something that looks like this window right beneath me right here. And I just went in and took this file right here, and then I printed it out, and I made sure that when I printed it out, I think I had to scale this one up 164%, but I made sure that when I measure that, that comes out to 100 millimeters long. So it's printed one-to-one scale, and I check in this dimension, 75 millimeters from end to end right there. So that's all good right there. Okay, now what we're going to do with this is we're going to slide that in underneath. Now you do want to watch when you do this, because the gearbox has, oh yeah, everything's really falling apart right on there now. The gearbox has these two little tabs on it. Okay, and it's really important that you put those tabs somewhere where you can screw that gearbox in, because there's not a lot of other ways to connect to that gearbox. So right now this has a little piece of plastic mounted on it as a bit of a standoff. You can use that as something to screw into, or you can now use these brackets to screw onto. This comes as part of your kit, but you need to have a firm and sturdy connection to this gearbox. And in order to get that, you're going to need to have a way to connect to these two tabs right here. And if you look at those two tabs right here, you can see that they're marked off right in here. So that kind of tells you which way up this gearbox should go, which means that on this drawing, it should be sitting right in here about like that, which is a little awkward and inconvenient for me, because I'd been planning on lifting this side up, sliding that down underneath, and tracing over those dimensions. You can get away with it when it's sitting in here this way. That shows through pretty nicely, but I'm going to have to go and print out a mirrored version of this, I think. That's going to be awkward. Well, for right now, I'm just going to flip it upside down. This still has roughly the correct dimensions on here. Hold that in place right there. Just remember that I'm doing a little bit of a cheat right here because I'm in the middle of filming a video. And so now I can line that up right in there. And that's a quick way for the students to get the dimensions of where that gearbox is going to go. And they can go over it and they can gently trace in where that gearbox is going to be. Now, for straight lines, you don't have to trace, just take a ruler right here. And it's important that they get this, because it doesn't leave a lot of room for all the fancy sheet metal work that their sketch told them that they wanted to do. Because everybody's got this really steep plow that comes down at the front, and it's harder to fit that plow in there than you think, because as you can see right now, we're already starting to bump up against some of the edges of our drawing. Oops. Just bump that. I should have taped that in as well, I guess. Okay, that's pretty good. And then let's see, we lined up with that axle right in there. We'll take that out. That's good. So now we've got an idea of how big that gearbox actually is. And so what are we going to do with that information right now? Well, now, if we're going to have a plow at the front, our plow had better not come right out to the 10 centimeter point. Our plow can be a piece of sheet metal that comes down in right here. And let's see, we're going to need something right in here. If I want my top sheet metal to come over top of that wheel so that the wheel doesn't get caught on it, I'm going to need my sheet metal to come right about in here. Now there's going to be right in here somewhere, that's that tab we're going to have to run a screw through, and that's going to have to connect to something. So I don't want my sheet metal setting right on there. I want a spacer and a standoff. Now, if I choose a reasonable height spacer or standoff, then it's going to be a lot easier to make. So we've got a lot of 1/8 inch material around the shop. That's 3 millimeters. And if we take a look right here, that's going to be 30 millimeters off the top. That might, right now we're sitting at 26, 27, 28, 29. I think what we want is maybe a slightly thicker spacer in there. Yeah, we can probably get away with a 3 millimeter. Yeah, we don't want friction against the wheel. Let's go with a 1/4 inch or a 6 millimeter spacer right in here. And so we're going to build a 6 millimeter block. Now you can also use this to add weight to the robot. So this could be a piece of steel, something that's going to go on there and just be machinable so that you can get your robot right up to that 500-gram weight. And you can see, because this is coming over top of the wheels, and there we go. All the weight is going to be right over the wheels as well. So we just put a note in there that this is the spacer. Okay, now our sheet metal then can come along over top of the spacer, and again, get everything squared up because you want to keep things nice and square. Really miss having the T-square right here, but oh well, we get by. Put this up right here, and somewhere right in here where that's going to come up. And then we've got about 1 millimeter of thickness for our sheet metal that you want to keep in mind. Okay, now down at the front right here, we don't want to come right to that 100 millimeter mark. We want to leave a little bit of space at the front for that. We want it to be as steep a plow as possible. So here's our bottom edge coming in right here. Now we can probably go about that steep. Right down to touch the ground. And now this is another little trick that you can do with 2 squares, as I just bring that back, and just to get my 1 millimeter of thickness for the sheet metal right in here. There we go. We've got some sheet metal coming right in there. And then at the very back, we'll just bring a flat flap right down as close to the ground as we can get. And so let's just line that up. Make sure that you're not impinging on the chassis. Bring that down right close to the ground, maybe just a millimeter or so off the ground. And we're going to draw this corner as square right in here. But when you go to actually form that out of sheet metal, there's going to be a bit of a radius on there. Also up here, you're going to have a little bit of a radius form in right like that, because you're going to bend that out of a piece of sheet metal. And then you're going to have something on the side right here. Now you can either have your entire robot and the wheels and everything constrained, or you can kind of do like we did right on here and cut this piece up and use it to flap up and control what's up on the top. But now you've got the beginning of your robot coming together down there. And now it's time to take some of these dimensions and transition them into your top view. So you can start saying, well, what's the dimensioned top view of my robot going to look like? So again, set one square up as a reference, and then just come right up here. And this is going to be the front edge of your robot. Okay, this is going to be where it transitions right over the top right there. Okay, so that's the back side of your plow. I should carry that all the way through right down there to show that edge. Your axle is going to be right along this line right here. Front of your wheel is going to be right in here. Your rear of your wheel is going to be right in here. Bring that all the way down. And the very back of the robot is going to be right in there. Okay, so now what we're going to do is we're going to take this diagram again, and this time it's the right way around. Just going to peel a piece of tape up right here and slide this down underneath so we can see how much space. Okay, now watch, the where they've drawn the axle in is not actually the axle that we're using. We're using the axle line that runs right down the middle in here. Bloody tape gets everywhere. But it's still worth it to hold your piece, workpiece in place. And let's just square that up and put a mark right down. The middle of that gearbox so we can align things with your axle right on there. Because depending on which gear ratio you choose, you're going to get different places where the axle is going to be mounted onto your gearbox. Okay, now get that mounted in there, roughly centered. And the first thing you'll notice is that the default length of the axles is 100 millimeters. So you are going to have to cut your axles down at some point, and that will maybe inform your decisions. It's slightly easier to do it before you go putting your robot together. Okay, so that's sitting right in there, and here is the center hole for one of those tabs, and here is the center hole for the other one of those tabs. So you're going to have to allow space for that screw that we said. I got the position slightly off. The screw is actually going to be right inside here, inside your wheel. That's okay. That's going to work in a three-dimensional sort of way. And you can go in here, start tracing this out. Doesn't really matter if you get it all absolutely perfect right in there, because just so long as you've got the furthest back part, there you should be fine. And your mount points are going to be pretty necessary for you to get. And then you might just want to I'm not going to worry about all the little lines on the inside, because there we go. This represents the space that is being occupied by your gearbox, and your axles are going to be right in here, just a little bit to either side of that center line of the axle. Use the square to get this lined up. There we go. So that's roughly what your gearbox is going to look like when it's sitting right on there. This is the double gearbox. Like I said, this is the twin that I'm using right here. Double gearbox is a little shorter and a little bit wider. But anyway, we've got the twin in there, and I can pull that drawing out right there. And now I've got something to work around from the top view so that I can actually design my robot. So now that we've got this in here, we've got the axle aligned in the two different views. The next thing I can do is I can put my wheels in here, because of course whatever we build on the top has to work around the wheels. So the wheels, when they're seen from the side, are circular, but when you look at them from the top, they are going to be just a rectangle. So what we can do is we can come in here and let's pick a, I think I've been working from this surface a lot right here, so may as well keep everything square on there. There we go. And that line I've already done. I want it square to this side. Yeah. Let's just come in right here. And again, give yourself just a little bit of space to the inside of your 10 centimeter limits. That was about 2 millimeters in. We'll come about 2 millimeters in on this side as well. Yeah, you should probably measure it, but because we're allowing a little bit of room for slop, that's still going to be okay. And now let's say we want a 1.5. That's my standard tire width. May as well go with the standard tire width. It is about 13 millimeters is my standard tire width. Some might be a little bit longer in that size, so I'm going to allow for, there's 1 centimeter, 11, 12, 13. I'm just going to say 14 right in there, and then come in 10, 11, 12, 13, 14 right in there. And now so much easier to draw with the clear ones. I'll draw that right in there. Bring that back right to there. Ooh, off square. Broke my pencil tip. Blow that away. And now we've got our two wheels visible in the top view, and everything is fitting inside that shape that we're looking at right now. Okay, so now we can start thinking about the top view, or we can start thinking about, well, where do I want to put the batteries on here? We've got a couple of different battery packs that you can use. This is a pretty standard battery pack, so looks like that's going to sit nicely right in between the wheels. There shouldn't be a problem right there. Looks like it's going to fit in here pretty nicely as well. You can also go to a 2x2 arrangements for your batteries, so it's a little narrower right in here. Works nicely. Or down here, yeah, it's a little bit taller. Generally, with the mini Sumos, you want to keep your center of gravity nice and low, but sometimes, that all ends up having everything come out looking a little bit like a brick. I'll probably try something like this for this tethered mini Sumo. We'll see how all that comes together. Let's draw in what we want from a top view right on here. Okay, now I've got one line coming down right there. So where do I want the body of that robot to go? Now, if I want my wheels to be exposed, I can make a piece of sheet metal come down right in here and cut a slot for it on the side so that the sheet metal fits through right in there. If I want my wheels to be a little bit more shielded, I can come through just on the outside of them. There might even be enough space to slip a piece of sheet metal on the outside so that the wheels are completely covered up in there. It's kind of up to you if that's what you want. That might work. Or you can cut out a chunk and have the sheet metal come right over top of here so that your wheels are actually sitting inside fenders. We've got enough space right here. I think I'm going to run this over top here. We can always move the wheels back in a little bit if we start to run out of space. So I'll bring the sheet metal body, and I am going to just stick with a square piece of sheet metal on the bottom layer anyway. Okay, and just remember it's got a bit of thickness to it like that. That's going to come around right there, and then up here. Let's not do anything too fancy. And so what that's left me is that's left me about 1 millimeter of space on that side relative to my limits, and 1 millimeter of space on that side relative to my 100 by 100 dimensions that I drew in there to begin with. And let's just mark that in a little bit darker so that we can see the actual boundary of the robot coming together. So like everything in electronics, there's a fair bit of attention to detail there. I was a little bit off square, and if your students start getting a little too off square, you're going to start running into problems. Now I've got this spacer right in here, and that's going to come up as well. So we want to account for that spacer, and there's my reference line. So right in here somewhere, we've got the beginning of the spacer. And right in here, we've got the end. And so that spacer chunk might just come out. Just needs to come out past the edge a little bit right there. And just past the edge a little bit right here. That's how that spacer is going to fit into the top. And it's going to have holes drilled in it right there and right there. And our top sheet metal is going to have some holes in it. So what we're going to have down here is we're going to have a screw that comes up right through here. Oops. See, I knew we were going to need a nice clean eraser at some point, and I knew it was going to be worthwhile to keep those drawings nice and light. Eraser shields are really useful to have too. What I need to do is I need to bring that dimension right down here so I can see where that screw is going to be sitting. So that comes down right there. And we'll have a screw head come up right through there. The screw will go through, that'll be in behind the wheel. And we'll have a nut right down there. So that'll be screwed in. Of course, we won't see that because it's behind the wheel, but we're just sort of taking a look at where everything's going to be located right now. And we've got multiple layers of hidden lines, of course, that we'd be having to look at and think about. But if we've got, let's use this little battery pack right in here. Now, again, you can go online and you can Google drawings or prints or dimensions for these various battery packs and take a look at them. But this one is, let's see, that one's good. It's going to be a little bit wider with batteries in it. So let's say that is going to be 20 to, it's going to be, if we allowed 3 centimeters, by about 3 centimeters. 3 centimeters by 3 centimeters, looking at it, is going to be about fine. So find the middle of your robot right here, and let's draw a center line right through the middle of our robot. Right now our robot is, how many? I didn't want to do math, so I'm wimping out. Our robot's about 98 wide. So if I come to the 49 mark right on here, then I should be able to come in and, darn it, didn't get rid of that broken lead, left a little mark on my page. Yeah, that's about center line for the robot. So if that battery pack is going to sit right in here, we're going to have to create a new piece of sheet metal that goes over top of that. But that's okay, we know how to create sheet metal. And let's take a look right on here. So I said that's going to be 30. So let's draw that in at 15 millimeters on either side. And how long is it? We'll figure that out in just a minute. This is, by the time we account for the little battery clip that comes over the end, I'm going to say that that is going to be about 61 millimeters. Now let's say 62 just to be safe. And I am going to run that right to the back here. Where do I want that lined up in this view? If I line it up right here, that leaves me room for the sheet metal to come down right in here. So I'm going to line that up, yeah, right in here at the back of that spacer and come forward 62. Oh, that's going to be awkward. That's right at the edge right there. So I better move that back just a little bit. And as you can see, we're already starting to figure things out by putting this together. To make sure I've got enough room to fit the top down on there, I better set this back right about to here. There is my 62 for the battery pack. I need to take that line down here. There's the back of that 62. That line comes down. Better do that just a little bit darker because we have to reference that drawing right down here. There's our battery pack. Taking up space. On the top. Okay, and then the side view, we better give it 30 millimeters as well. So line that up where that comes down. And from the top of the sheet metal, that's going to be resting. 1, 2, 3. 30 millimeters right in there. And I was just blowing away a little bit of dust on there. From where that comes down right in there to this point right here. Easier to do with the clear ones. I actually have a clear ruler, but I use that one because it's got, well, it was made with a printed circuit board process, which makes it really cool. And that is where our battery pack is going to sit. And again, like I say, I left it a little bit long because we've got to fit the 9-volt battery clip on here. If you have one that just has wires coming off, it might be a little bit shorter. Okay, so if that's sitting right in there, then we can put a box of sheet metal around it. And that box of sheet metal is going to fit right outside of that. It's going to come right up in here. And alignment correct. So the inside will be right there. So I'm just going to stand that about 1 millimeter off. Bring that up about 1 millimeter higher right on there. And that's what that sheet metal is going to look like when we look at it from the side. When we look at it from the top, it's going to come in here, and I'm just going to make it a little box right around the top here. Stick to a common reference. And I've got a little bit more space up here on the top, so I am going to give myself just a little bit more width. Allow for the thickness of that sheet metal piece. Right to there. Right out to there. And then let's finish that up at the front right here. Okay, so I'm just going to sketch this in to show, again, the sheet metal will be bent this way, so it'll be a little bit rounded at the corners. So you don't want to build right to the dimensions of something, because if you're folding the sheet metal, the thing that's on the inside might not have rounded corners. You're about ready for a little bit of Bob Ross painting. Put some happy trees up on the mountain. And so that's one piece of sheet metal folded over right in there. Here's another. We're going to make that point nice and sharp at the tip. Depending on which gauge of sheet metal you're working with, sheet aluminum in 16 gauge, I think it is about 1.5 millimeters. So some of my dimensions might be a little bit off right here. But it's really important that you have the orthographic to work from before you start doing your layout drawings. Actually, I'm just going to use this to mark that in a little bit darker. Otherwise, I'll be here all day drawing that in. Yeah, we'll finish that up later. Okay, so there we go. We've now got side view of the robot. We've got this box sitting upright on here. And now our box for the battery pack is coming down. That line's right there. Oh. Let's make sure we get the back of it in here as well. This is the battery pack box looking down from above. Just want to make sure that that's clear enough for you guys to see. That's sitting right there. That's sitting right there. A little bit of parallax coming from the camera there, making it a little hard to see what's going on, but okay, we've got that happening right in there. And now we want this to be able to stay in place. So one way that we could get that to stay in place would be to fold tabs on there that just come out like this. And so that'll come right around there. And that will actually tie right in there. So we'll have this tab come down here. Let me just erase the head of that screw for now temporarily. And this is where I wish I had just a flat little eraser shield, but we'll fix that up in just a moment here. So that little tab is going to come down right about like that. Hold out from the sheet metal right there. And there's the head of our screw is going to sit right on top of that. So this piece right here is this piece right here in that view. And now that should all be able to fit together pretty nicely. Okay, so you end up with something looking kind of like that. Now, you can go on and you can develop an isometric drawing of it. And now that we've got the orthographic here, but what we really want to do is we want to get the layout diagram for this and figure out how it all comes together so we can actually make it out of sheet metal. I've put about an hour of yapping at you into this video. So you should be able to get a drawing like this put together in about an hour, I guess. And then we'll take a look at how we can extract information from here. We've already got the information that we need to know. Here's, a top piece. This is just going to be a box layout. We now know our side and end dimensions on there. So this will be a piece and we'll just flip the sides out like that, flip those sides out like that, add a couple little tabs right on there. So when we fold it up, we fold these tabs out. Actually, I think we fold the sides in first. And then down at the bottom right here, you're going to have a piece that comes out on the side that looks like this. So what you're going to end up with for your layout, you're going to have a battery box that's going to look something. There's the top of your battery box. There's one side of the battery box. You're going to have a tab there. You're going to have the other side of your battery box. You're going to have a tab there. You're going to have a piece that comes off the back and a piece that comes off the front. Those are all going to fold down. That's going to fold up. That's going to fold down. And that's going to form a box that fits on the top. And that hole right there are going to meet up with a piece that you cut out. Oh, now I'm drawing. What did I say we were doing for the sides right there? I think we're actually enclosing the entire wheel on this one. So it's going to look very much like that. And then we're going to have that battery box on the top. And that is unfortunately a little bit unaesthetic, sitting right in there. Comes almost all the way to the back, but that's the dimensions of what we have to work with. And then you're going to have this little tab sitting out right in there. But importantly, down inside here, your wheel is going to be touching the ground, and the bottom edge of your aluminum side piece is going to come up just high enough so that you've got that little bit of interaction between the tread and the ground. So there you go. You can get to different levels of detail on that. We've had students who've, I've had students who've come up with octagonal robots, all sorts of different designs and styles, and you can like I say, they've done a little bit of a unit on orthographic drawing. They know what they're looking at when they look at this. But what you have to tell them, okay, you have to force them to make sure that the wheel touches the ground and that the axle, okay, lines up with the center of the wheel and with the output shaft of your gearbox. If you do those things and they line things up like that, you're probably going to be just fine, and you're probably going to get a nice set of drawings from them that you can actually use to develop develop some sketches or develop some working drawings. But if you don't get that, you are gonna be in trouble. Took me a couple of years to figure it out, but I'm here to share that information with you, and there you go. So anyway, if you're feeling adventurous and you want to build your own robot and figure out how to do something like this, like I say, you're looking at developments on there, and you can do really neat things. Certainly you can do it in sheet metal and all the CAD tools that are out there. The sheet metal functions in Inventor, Fusion 360, whatever parametric CAD program you're using will work great. I may even get a chance to produce a video showing you how to use some of them. But honestly, when you're working with your grade 9s and 10s, which is where the Tethered Mini Sumo robot is really intended, they respond well to this because they're not worried about what they're doing with the mouse. Is it a right click? Is it a left click? Where's the icon or anything? They're learning some tools right here. And after you've drawn something like this with all the straight edges and that, and it comes together and it looks right and it actually works, you start to develop an appreciation for how people were able to do things like design the Spitfire fighter or the Mars lander. Those things weren't, well, the Mars lander was designed with CAD, but sorry, the Moon lander. Those were not designed with CAD. Those were all designed by hand, people sitting down and using classic techniques to put things together. It's not bad. Have a good day, and so long as you remember to put the wheels on the ground and the axle in the middle of the wheel and have it connect to the output shaft of your motor, you're going to be fine. But don't think the students will think of that on their own.